All right, before I start, actually, I may need some help with something. I know there are a lot of technically sophisticated people out here that maybe can help me with this problem, and since I'm such a Luddite, I got a new iPhone, but I didn't want that iPhone 4 because, people have trouble with the antenna, with the way they hold it, and it's expensive, and it seemed kind of complicated. So I went into Office Max, and I was kind of surprised that they had iPhones, and it was an older model, but it was a good price, so I decided I would get it. And the problem I'm having with it is that I can actually only get the calculator app to work, and maybe I need to schedule an appointment with the Genius Bar and have them show me, or maybe you guys can. But so it was great because it was only like $5. So it was obvious what this was intended to look like. It didn't say iPhone or iPod anywhere on the packaging, although Office Max actually did say iPod, iPhone, calculator on the tag on the shelf. So I've actually got a pile of these that I'm going to put on the prize table. It's actually it's a terrible calculator. And the finish is bad. It wears off, gets scratched up very easily. So I don't actually recommend it for any real application.
It's hard for people to steal. What's the TI model number?
So now be nice. All right. So those of you who've been before have seen my previous presentations on the DIY series calculators that Richard Otteson and I built. We started out using a PIC microcontroller, which is a simple, inexpensive 8-bit microcontroller. I'm going to go through these very fast because I don't really think that we need to go over all the details here, but we did DIY 0 that's hand wired, and that was not completed, but it got us to try to do a real one. We did a DIY 1, had a little bit better microcontroller, and it actually had a real printed circuit board, and Richard found a commercially available clamshell case, although we didn't actually use it as a clamshell. He cut it in two and used half of it. And so here you see the printed circuit board, the top and bottom, and in the case. You don't see it? Oh, I'm sorry. I'm one behind here. All right, there it is. And there's the original clamshell case, and we only used half of it. And so then we went on to the DIY 2. We used an even better version of the PIC microcontroller, had more memory, and we added a beeper so that it could make noise. The original objective, we started this back when it looked like HP's commitment to calculators was kind of flagging, to put it mildly, and so that was some years ago, and since then it's become apparent that HP really does still want to make calculators, so this is still just a hobby project. For this one, Rich came up with this idea of making a case out of laminated acrylic that's been laser cut. I'll show these when the lights are on, but I've got that one here, and some more photos of it. Then we went to the DIY 3 that really was only a minor variant from DIY 2. Yet another upgrade to the microcontroller, and changed the keyboard layout a little bit because we thought we might want to try to do a vertical format version of a Voyager, which has not happened yet. And the software improved. We did, the original intent was simulate the 41, but we only got as far as the Woodstock and 30 series. Turns out that the performance with this microcontroller was not going to be acceptable for the 41. The 25 runs about real speed. The 41 would be slower. The code is on an assembly language. If I did enough work hacking at it, I could make it run faster. Maybe it would be fast enough, but really I just didn't. Hacking on this assembly code takes too long, and I really didn't want to continue down that path. And so we also experimented with a few more case designs. The laminated laser cut case was very expensive to make, very time consuming. Richard came up with a laser cut and etched thin plastic case, a bent ABS case. I did a case on a 3D printer. So all these different approaches. We made a DIY 35, which was intended to function like a 35, and before the 35th anniversary of the 35, we didn't really get quite done in time. We had a red backlit LCD that had a reverse polarizer, so we actually got red digits on a black background. So it actually was an LED display in the sense that the LED was providing the red illumination, but the LCD is the digit mask. The drawbacks of the PIC microcontroller: it's an 8-bitter, it's too slow, have to do a lot of assembly language. I'd rather program in C. There is a C compiler, but it doesn't produce the world's best code. The PIC is a Harvard architecture processor, so it's not really well suited to C, although the PIC 18 is a little bit better than the earlier ones. So what we really want to do is use some other alternative. There are other 8-bit micros, but they have similar issues to the PIC. We'd really rather have a 16 or 32-bit microprocessor, execute C code efficiently. But the processor needs to be very low powered. Until last few years, really most of the 16 and 32-bit microcontrollers drew more power than an 8-bitter, and this is important for battery life. And also because we want the calculator to be compact, we don't want to have a bunch of AAA batteries in it because they are pretty high diameter. You can't make a thin calculator that's going to use AAA batteries. We really wanted lithium coin cells. So there are these new low-power ARM microcontrollers. So you all probably have heard about this Atmel part because it's used in a lot of the recent HP calculators. It's a nice part. It's very low power. It has a reasonable amount of flash memory. It has 6 KB of RAM, but only 2 KB of that RAM is battery backed, which is okay for doing relatively simple calculators. Not so good if you want a fairly sophisticated calculator. I'm not saying some of these new ones out of HP aren't sophisticated, but for things that you want more RAM, it wouldn't be good. You can use external memory, but you'd essentially have to access like a peripheral, and so it's not as easy to deal with the code. Then just recently, a company in Norway called Energy Micro introduced an EFM32G Gecko family of microcontrollers. These use an ARM Cortex M3, which is 32-bit ARM, but they only use the newer Thumb 2 instruction set. They don't use the traditional ARM instruction set. They have very high code density. They're low power. They have 128K of flash, same as the Atmel part, but they have 16K of RAM that can all be battery backed. Now I say can be in that you can actually turn off part of that RAM if you don't want all 16K to be battery backed and save a tiny amount of your power consumption. But anyhow, the 16K is enough to do what I wanted, which is a 41CX, 2 extended memory modules. There are a bunch of variants of the chip. Some have an integrated 160 segment LCD driver, which would not be enough for 41. That actually needs 216 segments. If you use a segmented display, it would be enough for a Voyager style calculator. Those use 100 segments.
Or a 10B2 plus.
Yeah, I believe this part would be suitable for all of the calculators that HP has done using the Atmel, although it wouldn't necessarily offer any advantage over those, except if you wanted to expand the RAM.
Yeah, just the LCD driver for the 20 and 30 wouldn't.
Oh, that's true. Those because those use more segments.
What was the price you were able to take those at?
In quantity 1, about $3. So.
Did you see any, hundreds of thousands?
No, have not seen the prices for high volume, and also have not seen, in high volume. Then you're talking about getting bare die for chip on board, and so you're going to save a little bit of money there too. So I have no idea how high volume pricing compares to the Atmel. So I got the eval board for this part in February. It's a board about yay big. It's fairly fancy. It has an energy monitor built in that shows you how much current it's drawing, kind of a waveform display of your current. It has the debug support, so you just plug it into USB and use all your normal ARM development tools with it. So the first thing I did was write some it has a whole bunch of power saving modes, and so I wrote some programs to test what the power consumption would be in different modes and at different clock rates. It has internal RC oscillators that there's a low frequency one that's around 32 kilohertz, and then there are I think 5 different choices between 1 megahertz and 28 megahertz for the higher frequency RC oscillators. And of course you can use external crystal oscillators for your 32 kilohertz or for normal speeds. Included on a keyboard matrix and a character LCD module, and started writing some test code infrastructure, wrote the timer code and key debouncer and display driver. I wanted to prove that we were going to be able to do a calculator and that the power consumption was going to be low enough to run for a good long time on the coin cells. And finally I convinced Richard that we should actually do a new hardware revision, which is our DIY 4. So I've got one of those here. It is not yet a calculator. I'd hoped it would be by now, but so we added we have a FRAM chip to add more non-volatile memory to it. We started the hardware design. I should say Richard started the hardware design in late July. We sent the PC board artwork to a vendor Richard normally uses for fast turn, and we expected to get that back near the end of August, which would have been plenty of time to get firmware working and actually have it be a calculator of some sort before this conference. But of course Murphy's Law steps in. So the printed circuit board company reversed our printed circuit board artwork left for right, which makes it totally non-usable. They tried to blame us for it. They said, oh, well, there was something wrong with the artwork as we submitted it. Richard submitted it the same way he always does. There's actually text on both sides of the printed circuit board. The text is backwards. It should have been obvious to the technician at the PC house that this was not right. So eventually they agreed it was their fault and they would replace the boards. And in fact they agreed when Richard said that originally we'd gotten the quick turn deal that doesn't come with a solder mask, which makes it harder to assemble. And they agreed that in fact they would even do the solder mask for us. Unfortunately, what happened is that wrong way. The new boards didn't arrive in time. They arrived after I got back. Richard's here in Colorado. I got back to California, trying to collaborate by email, and his schedule and mine are different, so trying to debug the thing and get it working. We could only get about one debugging turn a day. I would say, oh, we'll try this, and here's some new code, and it wouldn't be until the next day that I would hear back from, oh, I tried that and it didn't work, and this, that, and the other was broken. So test program works. Draws more current than I'd expected, more than the eval board did, running similar code, and so we've been trying to debug that. And all my attempts the next couple days after we got that working to fix it actually caused worse problems. So I learned a new German word, which is going to be very useful to me. And I don't know that I pronounce this right, but Schlimmbesserung, which is when you improve something so much that it's worse than it was before. And so those of you that have done any software development are probably aware that this is a very common thing, and so that's why I say I'm going to use this word a whole lot.
Does it have any sort of dirty or negative connotation?
As far as I know, it doesn't. And when I found this word on the internet, someone was suggesting that it was a relatively new word, but somebody else researched it and found that this word has been used in German at least 200 years ago with this basic meaning. So plans for DIY4, we're going to fix the power management issues, simulate the 41 CV, should be substantially faster than original 41.
When we say significant, 10 times?
At least 10 times, probably more. We can run this processor on the internal RC oscillator at up to around 28 megahertz. It can run to 32 with an external crystal. We're most likely not going to do that. Maybe we'll make some choices for the speed available. So anyhow, we'd like to eventually support a lot of the 41 features and options and so forth, but it'll take a while. So what everybody always asks me is, when can I buy one? And the answer is that probably never. The conclusion that we reached is that unless you are HP or TI or something, that trying to sell calculators would be a good way to make a small fortune, provided you started from a large fortune. The engineering of the electronics and the software is the easy part for at least relatively simple calculators. Trying to make a decent physical casing, industrial design that somebody would think is credible as a calculator, that they wouldn't laugh at it if they saw it at Office Max like I did with these iPhone calculators. Is a very difficult problem if you aren't making things in 100,000 quantities. And what I say, as far as could we do this so that we could sell it for a not totally unreasonable price? That's saying not what people in this room might not consider to be a totally unreasonable price, which by anyone else's definition that walked into Office Max would say, oh, that's insanely expensive. So obviously that won't fly. There's a little bit of a positive note on making cases, which is Tech Shop, which is this public access workshop in California that's very, very well equipped with machine tools and all sorts of stuff. Actually does now have an injection molding machine available for member use, and so I've taken the class on that and I'm qualified to operate it now, but the challenge then is making molds. Yeah, yes?
I was just going to say, to make a fairly bad mold but functional is actually pretty simple. I did it in school, in a class over the course of a semester. It's really just the time on the machine, which is kind of the expensive part, but it is definitely doable.
Yeah, well, but there's a big gap between something that I could probably spend a few weeks learning how to make a mold for something that's simple, and then making something that really is a good industrial design is much harder.